Okay, so this is attempt number 2 with this video. I'm not real sure what happened to the video that I made in class on whatever it was, Friday when we did this. So we'll go through this now. You'll get the Cliff Notes version this time around. What we did with this one is we found the derivative of e to the x, and we did this the long way, where we talked about the whole x plus an h, and then we wrote this as the limit of h goes to 0 with our function of x plus h minus f of x plus h over h. And then this is your function. This is your e to the x plus an h. So we then substituted those into those locations. So this became e to the x plus an h. Our function is just e to the x, and then all over h. From there, it was a little bit of a process. I showed something on the computer. It took some time for you guys that were trying to learn this, that were missing class the other day. It's not something I'm going to test you on, so we'll just cut to the chase a little bit. What we found when we did this process, and it took probably at least 5 minutes, close to 10 minutes to get through all of this, is that if I wanted you to take the function f of x equals e to the x, and we wanted to find the derivative, what we found the derivative of e to the x to be is itself. It basically reproduces itself. And what we then did, we kind of went to the calculator, we showed this, but what this is saying here is at the x value of 2, whatever f of 2 would be, the slope is the exact same value. So the y-coordinate on the curve is always going to be, at a particular x value, is always going to be the same as the slope of the curve at that particular x value. So we talked about how it's pretty straightforward and easy to remember. The derivative of e to the x is just itself. Okay. Eventually, I talked about how if there's a u here, all that means is your composite is not simply an x. And so down here, you'll see it's a 3x over a 2. It's a sine of x. So the derivative of e would always reproduce itself, but once it's a u, that's just indicating it's something more than just a simple x, and we have to carry out the chain rule. So then we would just do times the derivative of u. So long story short, the derivative of e to the u, it's going to reproduce itself. Whatever you start with is what you're going to get. And then we have to do times the derivative of whatever the exponent would be. All right. So if we go to number 1, if I wanted to find the derivative of e to the x, the whole basis of this is that it reproduces itself. The slope is the same as the y-coordinate. Number 2, now we do get a little bit extra where this is going to reproduce itself. Exponential always reproduce itself when we took our derivative. But then we still have to do times the derivative of the exponent. So if we look at this exponent, here 3 halves x, the derivative of 3 halves x would just be 3 halves. And then that's our answer. Number 3, e to the sine of x reproduces itself when we take our derivative, so you basically rewrite the original problem. And then the chain rule is just telling us now we have to do times the derivative of the exponent. The exponent's derivative, or the exponent is the function of sine of x. Its derivative would be cosine of x. 3, there was a little typo here. I wanted this to be an x, so if you can change your 2 to an x, that's how we're going to approach it. And then what we started to talk about, when we start coming across old rules, like this is a product rule. This is a quotient rule. This one is a chain rule. All those old rules are still going to apply. We just now have to know how to use those with the exponential function and its derivative. So for number 4, if I ask you to take the derivative, here's the product. First term is x squared, so that derivative is 2x. I don't know where the squared comes from. Let me get rid of that. And then you rewrite the second term unchanged. Then the product rule we add. So now this x squared stays the same, and we take the derivative of the second term, which is the e to the x, which we now know just reproduces itself. We'd still have minus, and then we still have to take the derivative of that x, which is a 1. And then that's it. So these two we got from doing the product rule with this product, and then still have the derivative of the x at the end. 5 is a quotient rule. This is one that I also mentioned. When we clean this up, you're going to want to know how to do this when we get to the test. There's a problem on the test. I'm going to ask you to do something similar. But the quotient rule, to at least get this started, is your denominator unchanged times the derivative of the numerator which is a negative sign. Then the quotient rule, we subtract, leave the numerator alone. And then we have to do times the derivative of our denominator. Well, the denominator is our new function, the exponential function. We know it now reproduces itself, and we have to do the derivative of the exponent, which is 3. Quotient rule, then we make one big fraction bar. We now divide it by the denominator squared. That's pretty straightforward in terms of the quotient rule with our new function. What I would then have you do, and understand this, here's this minus sign, big minus sign. So we have two terms. Here's our first term. These are multiplied together. And then here's our second term. And then they're separated by the minus. So it's a difference of these two. If you notice, each of those has a common factor of e to the 3x. So what I'm going to do is pull out that common factor of e to the 3x. What that leaves us with for the first term would just be a negative sine of x. Then we would have our minus sign. The second term would still have the 3 and the cosine of x. So that's the numerator with that e to the 3x pulled out. If you notice in your denominator, we have an e to the 3x 2 times. By pulling out that e to the 3x in the numerator, what we can now say is this e to the 3x is going to cancel with one of these in our denominator. So I'm just going to cancel this out. Instead of 2, we would have 1 now left over in the denominator. So our final answer would be a negative sine of x minus 3 cosine of x, all over now just 1 e to the 3x. So quotient rule with a little bit of algebra there to clean it up. 6, our next big rule is the chain rule. What we've talked about, even though this is a product between the 5 and the cosine, as long as the first part of the product is a constant, we can just drop that down and really just deal with the derivative of the second part. And the second part now being this cosine of e to the 4x. Chain rule still applies, so you're still going to do the outermost term first. That's our cosine function. So the derivative of cosine would be a negative sign, and then we know the inside should stay the same. Once we're done with the outside part, which we've now done, we immediately do times, and then we now go inside and take the derivative of the inside. We encounter that new function again. E to the 4x would first reproduce itself, and then we have to do the derivative of the exponent, which would be a 4. So our final simplified answer would be a negative 20 e to the 4x times the sine of e to the 4x. Okay? So not too bad. You just want to understand the exponential function, and the derivative produces the original function multiplied by the derivative of the exponent. All right, natural log of x, kind of the same thing. We're going to cut to the chase a little bit since clearly I screwed up somehow posting that video or recording that video. If I wanted you to take the derivative of the natural log of x, what we found through this proof, this one you could probably follow a little bit, is the derivative of natural log is always 1 over x. And what we talked about is, notice what x is. It's the composite of the natural log. It's the inner term of our natural log. So the derivative of a natural log is always 1 over its inside term. When we deal with that as the chain rule, the derivative of the natural log will, so here, the derivative of natural log will still be the 1 divided by its inside. So notice how the u is the inner term. But then, like every function we're doing, the chain rule will still apply. So we've still got to now multiply by the derivative of the inside, which would be your u. So that's where this little derivative of u over the change in x comes from. So again, really not too bad. If I ask you for the derivative of number 1, it's the chain rule. The natural log function is the outermost term, so we're going to handle that guy first. And what we set up here is the derivative of a natural log is 1 over its composite. So we first and foremost just do 1 over x cubed. That takes care of the outer term, and we now go to the inside and multiply by the derivative of the inside. So the inner term is x cubed, and its derivative 3x squared. So overall, the derivative is 3 over x when we simplify it. 2, same thing. Our outermost part of this function is a natural log. The rule for the natural log is its derivative is 1 over its inside, its composite. So that sets up the first part. Now that we're done with that derivative, we go inside and the derivative of the inside would just be 5 minus 18x to the 5th. Similar to number 1, you could write that as one fraction, but nothing really reduces there. So we just put this over the top of this, and then that's going to be our answer. Typically there, I ask people to do 3 and 4 on their own. If you wanted to pause me, see if you can get through that. 3 and 4 are pretty nice. If not, I'm continuing on. The derivative of that natural log would be 1 over its inside of 2x. And then the derivative of 2x should be 2. The 2's then would cancel, and our reduced version would just be 1 over x. For the natural log first is 1 over its inside, so 1 over cosine. Done with that part. And then we do times the derivative of the inside, which is a negative sign. This one I do ask people to simplify because what we should now get is a negative, and then the sine divided by the cosine is the tangent function. So that derivative ultimately gives us a negative tangent of x. 5 and 6, along the same lines of what I talked about with those exponential functions, if we start encountering product rules, which we do here, and the chain rule, which we do here in number 6, those rules we still need to recognize and need to be able to work with. So for number 5, we have 2 terms. Here's our first term. Get fancy here. Here is our second term. So it's a product between the x and the natural log of x. So just our product rule. Derivative of x would be a 1. Leave the natural log of x. Product rule you're going to add. Leave the x alone. And then we have to multiply by the derivative of the second term, which is the natural log of x. Its derivative is 1 over x, and then the derivative of x would just give you a 1. Plus, we still have this guy hanging out at the end. The derivative of that would give us a 1. These then cancel. So what our final answer ends up being is we get this natural log of x plus 1 plus 1, 2. 6, chain rule. So when we go to take this derivative, what we do is just continue with the whole outside to the inside thought process. This natural log is the outermost term. Its derivative would be 1 over its inner term. So its inner term is the entire natural log of 3x. So once we've done that, we've taken care of this guy. The next outermost term would be the next natural log. So we would then have to do times the derivative of that, which would be 1 over its inside. So that would be 1 over just the 3x. We're now done with this. Times our innermost term, which is just the 3x, and its derivative is 3. Much like that last problem, the 3 and the 3 in the denominator cancel. So our simplified answer would just be 1 over x ln of 3x. Okay, and then from there were 2 down here, 7 and 8. We just got one of those done in 7th period. We were able to get both of them done in 5th period, but you see one should be good. What I'm telling you to do is use logarithms to do the derivative for 7 and 8. Actually, maybe I do want to do both of these. If you can look at number 7, clearly there are no logarithms yet. So what I'm telling you to do, if I want you to use logarithmic differentiation, this basically means use logarithms to take our derivative. So what we talked about in class was we could do the quotient rule with this. At the same time, you'd be having a product rule up here. You'd still have a chain rule right here because of that half power with a fraction. It gets really ugly. So what we instead then do is we're going to use logarithms. So what that then simply means is we're going to introduce logs. So what that is us taking the natural log of both sides. On the left, that just sets us up with the natural log of y. But what that allows us to now do on the right-hand side is we now have the natural log of that mess there. From the day before, we had all those natural log properties, one of them being if I have the natural log of a product. So understand how we're multiplying these two quantities together right there. I can write that as 2 natural logs if I added those. So that's what we're going to do first. Another property that we had discussed in the day one notes is that if I am dividing, if I'm taking the natural log of a quotient, we could also do minus the natural log of our denominator. So we're going to do that next. So there were three main rules. If I have the natural log of a product, I can create a sum out of it, and we've done that. If it's a fraction, we can create another natural log by subtracting the denominator. And then the third major rule that we talked about that day, that was a review from last year, if I have a power, the natural log of something to a power, I can actually take this power and put it out in front. So that's our third thing that we're going to do. So we can then do that. And then this will be gone. And then now what we've done is we've created basically four. I'm hoping now we think what we did at the top of the page is pretty simple. Now you just have four of them. So this hopefully is pretty easy. This is its own natural log problem. This is its own natural log problem, as is this one. So now we just go through taking the derivative of all of those. So now I'm just going to put a big parentheses around this, say we're going to go through, take the derivative now of all four of these. So the first one, you would get 1 over y, and then the derivative of the y would have to be dy dx. Again, sometimes people wonder where that came from. It's just our chain rule. Here's the outer term. It's a natural log, 1 over the inside. When we get done with that, we now have to go inside, and the derivative of our y gives us the dy dx. Okay. This natural log derivative should be 1 over its inside. So 1 over x plus a 1. But then we know we've got to do the derivative of the inside, which is 2x. Plus the 1/2 we can drop down. And we just do the derivative of that natural log of x plus a 3, which would be 1 over the x plus a 3 times the derivative of x plus 3, which is just this 1. Last one, 1 over x minus a 1. That's the derivative of the natural log. And then the derivative of its inside, also a 1. What we then have done, we actually did this a couple sections ago in 3.7, we now just solve this equation for dy dx. That's our goal. We need to get this by itself. So in order for us to do that, we need to get rid of that 1 over y. So what I would now do is I'm going to multiply the left-hand side by the y so that this would cancel. But then what that would require me to do is do the same exact thing on the other side, which is to multiply that side by y. So in the next step, the dy dx will be isolated. I'm going to also simplify these derivatives. So this first one, I'll write a little smaller here, is the 2x over x squared plus 1 plus 1 over, I'll go ahead and distribute this 2x plus 6 minus the last one would just be 1 over x minus a 1. But then what we want to do is still multiply by this y right here. We talked about how, if at all possible, if we're finding, which we are, the change in y as it relates to the change in x, we would like all of our variables on the right-hand side to be x's. So this is good. These are all x's. This is good, all x's. And this has all x's. So we don't really want to put the y right here if we can avoid it. We would like to get rid of that and have it be something that's written in terms of x. So the way we can do that is, normally people don't like this, is we're going to do a substitution. So if I come back up to here, where I'm erasing to the original problem, notice we have y, which is what we need to replace here. We have that right here, and we want it to be all x's right here. Well, we have that. This is what y is equivalent to in terms of x. So our last step would be to come down here and rewrite what the original y function was. And then all divided by x minus a 1. All right. So that's the gist of that. I suppose I'll do number 8. If you don't want to watch it, you don't have to, but at least it'll be there if you want to see it get done. So the first thing I started out with, number 8, is we took this square root and we made it a half power instead. That's actually the first thing. Then we would have taken our natural logs. The natural log of y is what we would have on the left, but then we can now use our little shortcut, different color so we don't bleed on top of each other here. We can use the shortcut where, since this now has a half power, we can pull that out in front. So I'm going to pull the half out in front of the natural log of now what will just be x over x plus a 1. From there, we can go ahead and with our derivative. Or no, sorry. I'm trying to rush it a little too much. What that's going to allow us also do on the right is create two natural logs by subtracting the x and the x minus 1. So remember, if we're taking the natural log of a fraction, we can create two natural logs if we subtract those. And then they would each have that coefficient of 1/2. It's now at this step, we take our derivative of these with respect to x. So our outer term here is a natural log. We know that's 1 over y. Done with this, but then we have to take the derivative of the y, which is dy dx. Equals, now I'm just taking the derivative of this one. So the 1/2 is just going to get dropped down. The derivative of natural log of x would be 1 over x times the derivative of x. Then we go to the next term, take the derivative of this one. So minus the 1/2 gets dropped down. This would be 1 over x plus a 1 times the derivative of the x plus a 1. In the next step, same thing. I'm going to take this here. I need to multiply by y so that the y's will cancel, giving the dy dx by itself. But what that would also mean is I have to multiply the other side by y. That leaves us with dy dx by itself on the left, so that's good. That's our goal. As we go through simplifying this, this term here simplified would just be 1 over 2x. This term here simplified would be 1 over 2x plus 2, so minus 1 over 2x plus a 2. But then what we should now have is times y. But like we mentioned before, we would prefer this not to be y's. So if at all possible, which it is, if I go back to the original problem here, what y is equal to with respect to x is this radical expression. So we come back over here, we get rid of the y, replace it with the square root of x over x plus a1, and then this is our final answer. All right, sorry for the mix up with the videos. Hopefully that makes some sense. If not, reach out to me. I'm doing this early, what is this, Wednesday morning. So if you wanted to reach out with any questions, I'll be on our class link from 9:30 to 10. All right, okay, see you guys soon. Bye.